Hi, my name is Zach Horton. I'm a fifth-year PhD student in the Department of Statistics at the University of California, Santa Cruz. I've been at UCSC since 2019. I did my studies remotely during the pandemic, and now I'm set to graduate in the next 12 months, which is very exciting. I'm excited to share a bit about the research that I do on how we improve the ways that earthquake recurrence is modeled. So to begin, this project looks at a class of recurrence models called Markov renewal processes. The idea behind these is that you take a sequence of earthquake times and magnitude bins, and with a bit of restructuring, model the inter-event times and the transitions between successive magnitude categories. To help illustrate the issue that we tackle in this project, we use a data set from the Southern California Earthquake Data Center. The poster contains more details, but I should mention that earthquake magnitudes are split into low, medium, and high groups. Additionally, by visualizing the data using this particular diagram, it highlights a fundamental feature of Markov renewal processes. The event date and time are not themselves important, but rather the time since the most recent event. More important to my project, the observed magnitude is also not the focus, but the transition from the most recent category to the next. By breaking up the data according to their different transition cases, we visualize how Markov renewal processes treat each subset of the data independently. Is independence a reasonable assumption? The ultimate aim of this research project is to 1. Show the flaws of treating cases as independent, and 2. Develop a modeling framework that captures the underlying correlations and adjusts forecasts appropriately. The idea is a bit complicated, but it is to model the inter-event times for each transition case using a mixture tailored for earthquake models, which is already improvement over common methods that rely on simpler distributions. Then we allow the different transition cases to share model components using something called a correlated stick breaking process. The way we build this particular one is somewhat novel and contains some important special cases that are represented by these matrices. The end result, represented by this unfortunate bit of mathematics, is flexible, powerful, and provides a more realistic picture of earthquake recurrence. In analyzing the Southern California earthquake data, our proposed model has several advantages over current approaches. A big one is superior model fit, which is shown by these posterior predictive interval plots. The red bar in the center covers close to the target of 95% for each transition case for our proposed model, which is shown on the left. The two alternatives, in the middle and the right, are either much too small or much too large. There are several other measurable improvements that ultimately lead to more reliable insights in this study of California earthquakes. To wrap up, I'm very grateful to the ARCS Foundation for supporting this research, and we're excited to be submitting it to statistics journals in the next couple of months. Thank you.